Good evening, everyone, and welcome to our Rabbiteer session tonight. Deeper Dreams of Electric Sheep. I'm glad everyone made it through the traffic, and I hope you guys will have a wonderful evening. I have the privilege tonight to introduce Jade Abbott, our resident research lead. That's a joke. In all seriousness, Jade Abbott. She's our head of research here at Rabbit, and she knows pretty much everything there is to know about artificial intelligence. And tonight, hopefully, we will learn a little bit more about artificial intelligence as she's going to show us some really interesting things on the forefronts of what we can do today. Thank you, Jade.
Cool. Thank you very much, Celia. Jade Abbott, even. Okay. Cool, so thank you everyone for coming. Does anyone know what my play on words is in my title? Deeper Dreams of Electric Sheep? Anybody? No one reads? Come on. Say it louder, because no one else offered. Yes, so it's Philip K. Dick. If anyone's watched Blade Runner, you'll know where this actually came from. Now, the book's a little bit different to Blade Runner. I'm clipping. Is it fine? Okay. That's not fine. This, I'm going to put a button. Cool. So, so Philip K. Dick, if anyone hasn't watched it, it's about robots that are so close to, or androids, they're basically so close to humans they actually can't tell them apart. And they've got a long, long story about religion and electric sheep. It's interesting, so you should check it out. But that always brings to mind a couple of questions. Like, if we can make them an AI as close to humans, like how close can we really get? And I think traditionally we thought, maybe we can make an AI to detect things, but can we make it be creative? And if we can make it be creative, actually, what does creativity even mean? I don't know what's happening. Come on, computer. Here we go. Cool. So today I'm going to show you how an AI can try be creative, and you can actually make up your own mind on what that is. So first of all, we're going to go through the basics of what a neural network is. I'll do that really quickly. Who has been introduced to neural networks before? Hi. Okay, it looks like it's sort of 40% of you. Okay. Then I'm going to look at, if we're thinking about our eyes, how would a computer go about also having an eye to detect things? And then last of all, we're going to talk about a little game called the Art Forger and the Investigator. And what we're going to do there is actually train an art forger, or train something that can generate images in the style of something else that you train it on, which is quite cool. So first of all, this is Rabbiteer. We are at Team Retro Rabbit on Twitter, and hashtag Rabbiteer 2018 is our hashtag. I'm also, throughout this process of actually going and learning about GANs, I've got what they call GANs, Generative Adversarial Networks. I'm participating in something called 100 Days of ML Code. So in addition to the kind of ML work I do at Retro Rabbit, I go home and do at least an hour a day of some other field. And it's a really great movement, and I suggest anyone who is interested in artificial intelligence just participate. There's a lot of fuss about it. So if you want to check out my repo, I have code there. I also have daily updates of what I did, and you can see my trials and tribulations and struggles if anyone's interested. So let's talk about the basics, okay? Let's go way back. Let's say we wanted to predict whether someone was going to default on a loan. This is a very simplified example. We probably, as a bank, maybe have some knowledge about a person. So we've got their salary, their age, debt, credit score, probably whether they're married or not, a whole bunch of other things. And we also have some historical data about whether people defaulted on their loan. So what we want to do is try build a model that will, in future, given that we know salary, age, debt, and credit score, be able to predict whether someone's going to default on their next loan payment. They call each of these little lines there an observation. So a neural network would look a little bit like this. You don't have to understand the details too much. I'd rather you guys got an intuition for it, like a feel. And the feel is as follows. The idea is you want to be able to feed it salary, age, debt, and credit score, and out it'll say, cool, he's going to default or he's not. A little bit more in-depth stuff. So each of these little lines that connects these layers, they call them, is a weight or a number, and that's actually how the neural network learns. It contains all its knowledge in these numbers, and it needs to learn the correct configuration of numbers that will allow you to predict the final result. So let's say you give it a user, and it comes through and it says, cool, the neural network predicts that this guy is not going to default. Now, in order to train it, we basically already have a whole bunch of data, historical data of people predicting loans, well, not predicting loans, people who have defaulted on their loans. So we feed it data, the neural network will make a guess, basically. That's what it is, a mathematical guess. And we'll say, cool, this guy's going to default. But we know that he didn't default, so then the neural network would have to go, okay, let me adjust my weights a little bit. And you feed it the next guy, and he says, cool, this guy isn't going to default. And then he is, and he says, okay, let me adjust my weights a little bit more to make that outcome more probable the next time. And that's kind of the gist of a neural network. So once again, the basics, you kind of initialize these weights randomly. It's a random guess. It starts out knowing nothing. You feed it some input. It kind of guesses what the output should be. Then you kind of compare the error and the guess, the target, the correct output, predict, maybe that's he's going to default on his loan, and the guess, which is he isn't, and then you calculate the error, and then based on that error, you can now make adjustments to your weights, so that next time the correct output's more probable. And you repeat this time for every single data pattern that you've got in your set. So that was neural networks in 5 minutes. Did anyone follow? It's a very intuitive feel. Now, we could go through the mathematics, but that would make a really boring lecture. This is not a lecture, this is a talk, and I'd like you to afterwards be able to still be inspired enough to go do it yourself. And if I spent half an hour explaining the mathematics behind it, you might be a little bit afraid. There's nothing worse than looking at maths on a board. It puts you back in like high school days. Cool. Now, that's the basic of a neural network. Now we're going to take that kind of same idea, and we're going to train an eye. And our eye is going to basically be able to detect different things. They call these convolutional neural networks. If you think of an image, so this is an image from the very well-known IMNIS dataset. It's a picture of an 8. And first we'd need to look at that from a number perspective. So obviously each of the pixel values result in some sort of number. Now, if we're doing a normal neural network, we've got this line of inputs, and each little pixel will become an input point. And you could make that in a line. It would look something like that. And you'd be able to have your input nodes, you'd have a whole bunch of intermediate things, and then it would predict the likelihood of it being an 8 or not. Now, the problem with doing this, let's make everything a single line or a single vector or a single string, is that we kind of lose something about the image in doing that. When we look at the image, we know it's an 8 because we know we can spatially group it. We can see, these areas are grouped together. This little corner's grouped there, and this little thing's there, and overall they all interact in that way. So instead of giving it these kind of just flat number of integers and expecting it to learn, I'm losing my mic. There we go. We're instead going to do something a little bit more intelligent. So this is a convolutional neural network. It looks horrifyingly scary. Each of those little windows is kind of a layer. And we'll go through the pieces that kind of make up this convolutional neural network. You can see at the input you've got some sort of picture, and the output we've got 4 features. We've got dog, cat, boat, and bird. So this is what it knows how to output. So right now it's deciding between whether this input image is going to be a dog, a cat, a boat, or a bird. So what are the different parts here? First, you've got a convolution, which I'll get to. Then you've got something called pooling and something called classification. And if you look at the image, you'll see there's a lot of repeats here. You've got convolution, then pooling, then convolution, then pooling, and then fully connected, which is actually the classification part. But the entire thing is just made up of these 3 guys, right? So what does a convolution do? A convolution tries to extract features. And by feature, I mean, think of like a little corner, or a little line that tends towards the left, or a little line that's horizontal, or a little line that's vertical. And perhaps you'll see we'll start to accumulate into bigger features, so corners and circles and shapes. And the idea of a convolution is you want to preserve that kind of spatialness. between the pixels. They're not just one giant vector of numbers. There is some sort of relation between them. So this is what a convolution sort of looks like. So let's say you've got a 5 by 5 image of pixel values, which can either be 0 or 1. So this is a very small, simple image. You take what we call a filter. Now, for the sake of this example, we're using a 3 by 3 filter. And what we'll do is we'll basically, that filter, they call it a feature detector. They're basically going to take that feature detector and run it across the image and see where it matches. And when it matches, it'll record a higher value. And by match, they're actually using a very basic dot product. So it's basically the dot product between all the values in the filter and all the values in the image at that point. So if the feature is definitely there, then it results in a very high value. So that's what they do. They've got the image and these filters. And you end up with multiple of them, actually. What's cool about the filters is that you don't have to explicitly create them. We don't have to say, oh, we need to look for these type of little features in the image. The neural network is able to learn what those features look like through its training process. So this is quite a cool demo. So you can see, if you can see, this is like a little line slanting that way, and what it's doing is running across the image, and it generates that. And what it does, the output of this filter image and filter running across is what we call a feature map. That's basically saying where does the feature occur. And you'll see it's darker where the feature actually does occur. Cool, so that's convolution. That is the main important operation here. But it turns out our eyes do a little bit more than that. So if we were to track every single pixel exactly, we probably wouldn't be able to generalize very well. So one of the things we want to do is kind of make it a bit more robust against this small transformation between images. One of the things we can do is reduce the other side effect is that we end up with a lot of parameters that need to be optimized. So if we can reduce that, that's really helpful. So pooling is actually quite simple. We take one of the feature maps, or the rectified feature maps, and what you do is you just look at that a little block and you say, cool, what's the max value there? And that becomes your new value. So what we see is we're taking a very high dimensional 2D matrix and we're actually making it a lot smaller. And in that we lose kind of some details which actually help us classify. Cool, so now we pair these in layers. So we have convolution and layer, and then a pooling layer, and then a convolutional layer and a pooling layer. And in this image you can see our first layer, the features are very small. These little filters are very small, little fine-grained lines. And in the second layer we're starting to pick up eyes and shapes and noses, and then in the third layer we've got actual faces. Now, in practice, this neural network's actually a lot bigger. There are probably 12 layers in this neural network that are generating images like that. And that's one of the big complexity things. That's why all of this is only happening now. A lot of these concepts were come up with many, many, many years ago. But because we've now got an amazing amount of computational power, we can start using these techniques. So we've done convolution, we've done pooling. But how do we actually classify? So, going forward. The classification is similar to that first neural network we saw, just fully connected. Every node in the image is now connected to every output node. You've got some sort of function running on that. And the training process is the same. You feed it an image, it outputs a prediction, and then you adjust the weights to make the correct prediction more likely and the wrong prediction less likely. And we do that, and usually this takes, and this is a criticism of deep learning, it takes hundreds and thousands of images to get this. What's great about this is you can actually download some. So you can get pre-trained images that you can download, so pre-trained models rather. So you don't actually have to go train these yourself. They take weeks to train, the really, really big ones, the really generic ones, because then you need a lot of images. You can go download one. There's a really good one called VGG. There's another one called ImageNet. And they're quite powerful, and they're pre-trained, and they have the weights, and they're for free. And you can go and use them in your own project, assuming you have the correct type of data, which we won't even go there. I've got another talk on that. Cool. So we can kind of now see how we can train a model using a neural network. we can see, we have an idea of the eye. Does anyone have any questions so far? Reinhard, yes. There's a microphone for this. No, you can't take this one. No, please don't take this one off. Oh, you want to fix it? Oh, you can ask the question.
So just to clarify, in the convolutional neural network, does it only train a fully connected network?
Trains everything, end to end. Yeah, so it back propagates through all those layers too. So if anyone's done neural network in more detail, you'll know about back propagation. It actually, that process runs through all these million layers. There are a couple of changes to your training. So if you know neural networks, you use something, you don't use sigmoid. That has a couple of problems. It suffers from something called the exploding gradient or the vanishing gradient. So you use something called a rectified linear unit, which enables you to train better, which is cool. So, we've got an eye, so we've got something that can look at images and spit out an answer. But that's not what we want to do. We wanted to have some sort of image. We wanted to have some sort of features, noise, whatever. Doesn't even matter. We just want this AI to be able to create images in a style that we want. So this is where a generative adversarial network comes into play. In particular, we're using one called the deep convolutional neural network. It's not the original one, but I think it's the one that was published soon after. And now we have this play. So this is my beautiful drawings. You can tell that that's the artist because he's wearing a beret. And this guy is our critic or investigator, and he's got a magnifying glass. And if we think about an art forger, what they'll do is forge art until some investigator picks up there's a problem. Same with faking money, right? They pick up, oh, wait, I see where he's doing. And then the art forger has to become smarter, or the money fraud guy has to become better. And then the critic becomes better, and then the art forger becomes better. It's like with security. We put up security, they find ways around security, and then you make more security, and criminals find ways around that. So it's kind of this competitive game we play. So the first bit we can talk about is the discriminator. So to give a high view of the process, this is what we're going to do. We're actually going to take two neural networks and actually play them against each other. One's going to generate images, and the other one's going to determine whether they came from a real source or not. So, the discriminator. Input, you give it a picture, the masterpiece. It'll inspect it in the same way we've actually seen. It's a normal convolutional neural network. And it's going to output whether it's fake or real. So we're going to train it on a whole bunch of real images, and we're going to train it on a whole bunch of images that the generator made. Then we have, you don't have to worry about that too much, because actually the architecture you've already seen when I talked about the eye. Here's where the weird stuff happens. This is the generator. The generator takes random inspiration. You know, that's how art happens. You get randomly inspired. I'll talk a little bit about, you could take more than just random inspiration. You could take, you know, some sort of embedding of the lyrics and then generate the album cover, which would be quite fantastic. But this is as far as I managed to get. So next presentation, we'll do that. This one, we're going to take random inspiration, and we're going to try and generate this masterpiece, which will be our little album art. Cool. So this looks a little bit different. So the convolutional layer was the other way round. So here we start with some sort of noise. That gets made into filters. This is basically, that little cube is a set of feature maps that are together. And so we actually have 1,024 feature maps. And this is kind of the numbers and the scale you're talking when you're doing convolutional neural networks. Then it gets a bit fatter and the image gets a bit bigger, so your maps get a bit bigger, and then right at the end it actually outputs an image. We're going to work with 64 by 64 bits because GANs are notoriously unstable in higher dimensions. There are ways around this. I never got there, so we will get there one day. And you can see it's a depth of 3 because there are 3 channels, so RGB. Once again, this little bit here is our inspirational noise, and that's going to be our masterpiece. We've got this thing called a conv1, conv2, conv3, conv4. This sounds like it would be a convolution that we've already seen. This is actually kind of like the reverse. It's called a transposed convolution. And it kind of does the reverse of pooling. So it'll take something of smaller dimensions and make it bigger, and it will take filters and make an image. So in order to do this presentation, because I've played around with GANs before, but not in like much depth, I had to now come up with my own architecture and put it together, and I was using bigger images than most other applications did. I actually ended up having to read a paper on the arithmetic surrounding how you make that graph. So we've got 1,400 filters, and then that gets slightly bigger, and that gets slightly bigger. So if anyone wants to go build their own, I'd recommend A Guide to Convolutional Arithmetic for Deep Learning. It is amazingly presented. This is where I got these images from. And this is what the transposed convolution sort of does. So it takes a very small image, right, and tries to generate the bigger one from it. And you can do it in different ways. So this one's got something called stride 1, and this has got stride 2, which I'll talk about when we actually hit the code. Cool. The training. How does this work? We've got these two weird neural networks. How are we going to train them against each other? So first we're going to give the discriminator a batch of real images and a batch of images generated by the generator. And we're going to train it on that batch. Makes it a little bit smarter. Then we're going to freeze those weights, and we're going to train the generator. We're going to feed the generator, ask it to generate some noise, and feed it all the way through. And the discriminator is going to go, okay, cool, this is or isn't a real image. And every time it says, no, it's not real, the generator needs to now go adjust itself to become better at generating those images. So it goes, oh, I'm not fooling this discriminator, I'm not fooling the investigator, I need to change my art to be better. It looks a little bit like this. So we've got some real images. These will be album covers, real ones. Got some noise. Generator takes noise as input, outputs some sort of fake image. You'll see at the beginning these are they're kind of grey, they're very random. Together, you feed these to the discriminator as a data set, and you tell it, okay, cool, these are the fakes and these are the reals. And that's how you just train the discriminator. And I said we freeze the weights of the discriminator, and we take noise, generator generates some fake images. We tell the whole model, because they called it combined model, we actually put them together. We say, cool, we know these are fake, but treat it as if it's real. And when you don't fool the discriminator, you're going to have to adjust your own weights, because we're not going to touch the discriminator weights. And that way the generator becomes better and better at faking it. Cool. So GANs came about a couple of years ago, and there have been multiple variations and different types. So I'm just going to run through to show you the sort of weird stuff they do. And I have to say, a lot of it is alarmingly weird. There's a concept called the uncanny valley. And in the uncanny valley, it's like when they try and make those realistic robots, and you feel a little bit irked out. Like if a robot looks like a robot, that's fine. If it kind of looks like a human, you feel uncomfortable. And it's the same when you're talking to a chatbot, and it's kind of like a real person, but it's not. It also kind of falls into that uncanny valley where you're close enough, but not, and you're pretending to be a human, which can be a bit scary. So I find GANs, or generative adversarial networks, suffer from that. So you can do kind of some weird things. You could give it a picture of zebras and ask it to generate pictures of horses, or vice versa. So you kind of train it to generate things like that. This one's quite cool. You basically train it on a bunch of buildings, and then you train it to, given some sort of condition, so we need the image to look like this, try generate an image like that. So you can see here they've kind of got the plans of what this should be based on, and then it tries to generate an image based on that. So they'll give it, like, train it on images like this, and then it'll be able to generate its own images. This is a really cool application. You can see it, they struggled, but you'll see now, so did I. They're trying to generate 8-bit pixel art for video games, because there's a lot of it, and I'm pretty sure it takes a lot of designers' times, and sometimes you don't have a designer. So it wouldn't be cool if we can just train, a GAN to generate our levels. There's a great blog there. It's called Abusing Generative Adversarial Networks to Make 8-bit Pixel Art. I think you should read up on it. It's a great representation. And you can see it's actually struggling to make pixels, but it has done something unique, which is cool. These don't look quite like anything else that it's been given. This is one of the cooler ones I've seen. They give it people's faces at different ages, and they actually use a GAN to age the faces. So you give it a real face, and then it can learn how to generate a older face from that. And this works pretty successfully, and it's actually quite a hard thing to do. This one's cool too. This is image completion. So you can actually see they block out the eyes. I quite like this one. They block out her sunglasses, and it generates eyes where they should have been. I think this is really cool. Sometimes it does quite similar, sometimes it doesn't. Here, they generated him without glasses. And it seems to respond to like a whole bunch of things. Here's his eyes really squinted, and obviously they were trained on things that weren't, and that's pretty realistic. So it doesn't know what these people look like. It's just learned from a lot of faces that this is how you'd complete it. This one was a video, but I don't know if it's moved as a video. Oh, damn it. Didn't paste it in. So this one is really kind of cool. So you can't really see, and I thought I didn't paste it in properly. But this guy kind of sketched a 2D image, and over here it's trying to generate a 3D representation of it. And you can see he'll drag it around, and then if something's wrong, you just kind of scribble more there, and it fixes it, which is quite fantastic. This is a tool you can go download and play with, apparently. I haven't done that yet. I didn't change the title on this slide, but this one you give it a damn scribble, and it generates magnificent art, and I think with amazing effect. Why are you laughing at me? It's magnificent. I put this on a wall. Shut up in the cheap seats. Why don't you? That's my father, so I'm allowed to say that to him. So yeah, now that I've shown you a bunch of weird stuff it does, let's make one ourselves. So I want to generate album covers, so I've got some data. You can go online and get this data for yourself. There are 148 gigabytes of album covers. That's a lot, and I didn't download all of it. Thankfully, you can download individual parts. So I downloaded the, which has about 60,000 images. Then I think A is quite big, and if you want to download a really small set, I'd suggest X or miscellaneous. There's a lot of duplicates, this is the first time I've processed data where I didn't actually have to use pandas or some data science tool to pre-process it. There are all these beautiful Linux command line tools which are substantially faster. So certain things like your EXIF data, which is your metadata for your image, they can be messed up, and then your loader doesn't want to load it in, so I had to remove that. Remove images that were just totally corrupt or broken, and remove duplicates. And thankfully, there were just Linux tools waiting for them. So this is a sample of what the data looks like. AC/DC, pretty straightforward. Some weird Asian band, we don't know. I don't know, I can't even read that. And we get a lot like this, right? So a lot of things don't have covers. And you'll actually see that in the GAN. It tries to generate these type of images because there are loads of them. So you've seen this picture before. This is our generator. This is the exact architecture we actually used in our generator, with all its little convolutions. And our discriminator looks similar. So this is the normal convolutional neural network, which starts with an image and outputs yes or no. Cool. If you downloaded my code beforehand, I don't know if I shared the code. I think I shared everything else and not the code. You can go download it there. We've got, it's in Python 3. It's using something called Keras, which is a beautiful high-level layer on top of TensorFlow. TensorFlow is a type of library that makes you feel stupid. Yep, I feel pretty stupid. And we're going to do something called a deep convolutional GAN. There's a repo again. And I'm going to go through all this code, and afterwards I'm going to tell you that it doesn't work so well, and I can't figure out why. The architecture is exactly the same as the second link here, which is the code I was actually basing it on. It's written in TensorFlow and not in Keras, which is why I'm feeling very stupid right now, because my Keras code won't even work. And I think it actually illustrates something at how difficult these networks are, and how unstable, and how much research there still is to go. So I'll be looking at two sets of code. I'll be explaining with this one, because it's nice to explain with, and then I'm going to demo with this one. This code actually does work to a point. The images just, the training was very slow, and I couldn't figure it out. Okay, let's go look at some code. How is that size, or can we make it bigger? Bigger? Big enough? I think it's big enough. Cool. So this is our DC GAN. It's written in Python, like I said. And I'm going to first look at let's look at our discriminator code. So here's the code. So when I use something called conv2d, that actually encapsulates both the convolutional layer and the pooling layer. It's actually built in. Wondering what kernel size is? That's the size of the little filters that run across. You're wondering what strides are? That's by how much does it shift that little filter each time. Set some shape, and they've got something called padding called same. Padding is basically how far do you go off the edge of the image. Because sometimes it could be a feature right at the end, and you actually want to look a little bit further onto the end of the image. And you've got some sort of initializer. The initializer is just to initialize all the weights in our neural network. We usually like to make them very small values for training. Then we've got an activation. Now this is what happens as you put all these things through, then you now need to apply some sort of mathematical function to transform them. And in deep neural networks, we like using something called ReLU, and in this case, they use leaky ReLU, which is just a small variation. And you'll see in the code, if you go through it, I provide detailed explanations about how the people, about how I don't understand why they used a leaky ReLU, and how the people who trained the neural network also weren't sure why that worked better. And this is a lot of AI research. They're like, we tried this, it worked better than the standard way, and we don't know why, but we're going to tell you anyway. Some sources made up stuff. Well, I don't know, there were sentences that didn't make any sense. I've read the sentence, I've made a couple of other people read the sentence. Julian doesn't know what they mean either. So some odd things there. So that was our first layer with some maths after it. Then we've got another convolutional layer. You can see that the size is the depth. This is the depth of that little tensor. Is a bit bigger. We keep the same kernel size. Everything else is the same. And we add a step called batch normalization. And batch normalization is actually a way to speed up training, increases stability, and it's a lot to do with the mathematics. So for those of you who know neural networks, you probably know about normalizing your inputs. So your inputs come in, they're between 0 and 4,000. And actually, it speeds up training if you make them between 0 and 1 or 0 and 0.5. It's quite a fun value to tweak. So batch normalization does the same, but to the intermediate layers, and that makes everything a lot faster. I've got a really great explanation here. Towards data science, I do a lot of really cool blog posts, and batch normalization in neural networks is a really, really good one. They go to it in depth. It's the sort of topic you'll be like, oh, this will be easy to read, and then you realize it's a minefield of detail and really well researched. And we shove in another leaky ReLU, got something called dropout, which does the same sort of thing to batch normalization, except it's got to do with freezing the weights sometimes to make it generalize better. And then we repeat that, and you can see each time our depth gets a little bit bigger. So that's a lot of code. Cool, so that's like 4 or 5 layers, and right at the end, we flatten them. So we've now got a 2-dimensional matrix. We now want to flatten that into a line, basically a single set, because that's what our dense networks look like. And we want it to predict one output. That's what dense 1 means. And on that, we put an activation called sigmoid. So that's a mathematical function that kind of runs between 0 and 1, and that'll output true or false. It'll actually output a number, and then you actually threshold it to say, okay, this is closer to 1, therefore it's true. This is closer to 0, therefore it's false, and the maths actually takes the error into account. Cool. Our generator, our discriminator. So that's the one that decides whether the image is good. That's the easy one. The generator gave me nightmares because I could not get the architecture right for very, very, very long, because you have to basically read the original papers to understand it. Cool. So the generator is the one. You give it some random noise. So you'll see the first layer takes an input of latent dimensions. This is what we're going to set as how highly dimensional is our random noise. Give it a large vector of 100 floats, because why not? You can choose 50, you can make it 2,000, doesn't matter. Then basically morphs that into the first layer. So it has a lot of takes, yeah, so that's that, and then outputs this quite large number, which is actually 2000, I think it's 2024, 1024. And you do a reshape into your two-dimensional vector, then you do the same kind of thing, some batch normalization, and now we're going to use an activation called ReLU, which is actually the simpler version of the leaky ReLU you saw. It's used commonly in neural networks. It's good for deep neural networks, which is what this is, where you've got multiple layers. And here's where the real magic is the convolutional 2D transpose. And this one, I'm, like I said, you can even see on my slides, I'm still figuring it out. It's quite a hard operation, and even harder to describe. And it, like I said, sort of does, they used to call them deconvolutional neural networks, and they like a deconvolution rather than a convolution. Then someone was like, no, it's a bit of a misnomer, it's not doing that at all, what you think it is. So everyone stopped. And once again, we have a couple of layers of those, right? And at the end, we need our generator to output a single image. And they tan H that, which basically returns a number between -1 and 1, which is why, as you'll see later, we scale all the input to also be. So the real images will also be a value between -1 and 1. Once again, why tan H? Why not sigmoid? Why not ReLU? They just found it worked better, and that's why they used it. And no one really knows why. If anyone does know why, please come tell me, because you know way more than I, and I've kept trying to look. Apparently, it actually helps it cover the image, the color space quite well, whatever that means. I don't know. Then we output the model. Model.summary is just basically outputting the model, and you'll see later. And so that's a generator, and that's a discriminator. Just to quickly go through the initialization, we're using an optimizer called Adam, for those of you who care. I'm going to build the two discriminators. So we've got the generator and the discriminator. Then we're going to create a third complete neural network where your discriminator is set to default. And we call that the combined model. So now we actually have kind of three. We've got a generator, discriminator, and one that's got both of them, but a discriminator that won't change. Cool. Let's look at training. And what's cool about this code, and what's cool about Keras, is it's less than 200 lines. Okay. So we first, don't even have to initialize that. First, we send through the discriminator. So I've got a data generator. Generators are really cool. They're a thing of Python. It basically gives me a batch of images at a time, and without putting pressure on all your memory. So what you'd usually have to do back in the day is you'd load all the nonsense into memory, and then you'd have to train it. And if you've got 148 gigs of it, that's not going to work. So what generators make it really easy to just load a batch of it, use that in memory, then just kind of discard it, and then load the next batch into memory and use it and discard it. Cool. So we select a random batch of images from our real image data. Then we generate an equal number of fake images. So we tell our generator to predict based on some noise that we give you. And like I said at the beginning, it knows nothing. It's going to generate sort of gray patches, you know. Then we train the discriminator on the real images and the generated images. And then we just kind of average the two loss functions. Loss functions is that error I was talking about. Cool. So then we train our generator. And our generator, we take the combined one, we give it the noise we had originally, and we say these images are valid, even though we know they're not. And we train like that. And we train it again, twice, not because the paper said it, because one of the implementations I read said we should, and that would make it better. Because what the problem is that, let's say you've got these two competing models. What if one of them wins, and just completely wins all the time? And what happens is your neural networks actually stop learning against each other, because this one can discriminate really well, and this one knows nothing. And it actually, I think they call it the model folding. You see, it actually doesn't train anymore. I'm going to plot the progress and save some of the images as samples, and that's the basics of it. I'll quickly have a look at the main. You can see we set up what's called the image data generator. which is amazing because there's no processing of anything hard. We've got something called flow from directory, which says, look over there, transform the images into the correct size, and then pipe them through your process, which is outrageously cool because trying to do that yourself is really painful. So with one function, we can resize the images, rescale the images, and everything. Cool. I do a little bit of a thing, so it allows you to rescale between 0 and 2, but I cannot shift those inputs between -1 and 1, so I kind of wrapped that generator and made it also do like shift them into that kind of range. And then we train it, and the training is just .train. There we go. We give it the data generator, we give it the batch size, which I think is 64, and we give it a save intervals. How often do you need to save it? And then right at the end, it saves the actual model, so we can load it in, which is cool. But it doesn't work so well. So it did kind of work. We got some images. I think some of them are here. I'll quickly show you those, and then I'm going to show you the other code. So they tend to start out looking a bit like that, which is kind of wrong, and this is a bit I haven't solved yet. This was a broken time when I was actually doing something wrong. And then if you look at something like that, that's one single image. You can see it's kind of learning colors, but it's doing it really slowly. This doesn't look anything like an album cover. It looks kind of like some gradients. So after lots of fights, I eventually gave up, and I moved on to another amazing thing called, well, this other DC GAN implementation. What's great about this is that in order to use it, you've got a great command line interface. So you can actually feed it, like, look in this directory for my images, look over here for my, here's some parameters. This is the image sizes we're going to be looking at. And it actually does everything else for you. So I'm going to have to SSH back into my box. So I'm running this all on AWS. You can have a GPU machine. It's really annoying to run it on your laptop. So I wanted to get a cloud machine to do it. I actually had a really fun time trying to get one from Google and trying to get one from Azure and trying to get one from, there's another thing called PySpark. And then other ones were like, and the reason that is Bitcoin. So now everyone wants GPUs to be mining Bitcoin, but the cloud providers are like, yeah, but then we don't have GPUs doing anything else. And I think that bothers them. And I think it also becomes quite expensive even for them. So that was a bit of a process, but I eventually got one from Amazon, and they've got really great images. So you can be like, cool, I want a deep learning box. And you click it, and no root to host. Am I not connected to the internet? I'm on always on. No wonder it's been loading badly. There we go. If you're wondering, the machine is named Christopher after Alan Turing's machine. I later found out that they didn't call it Christopher, and I can't remember where we heard that. And my boyfriend pointed out it's actually called Bomber, is what Alan Turing's not computer decoding machine was. I tend to name all my computers after like famous servers or whatevs. Cool. So when you log in to something like this, a nice deep learning AMI, they actually give you a whole bunch of virtual environments. So we've got one for MXNet, which is Amazon's library. We've got some for TensorFlow, both Python 2 and Python 3, Theano, PyTorch, CNTK, Caffe. There are also providers that provide you what's called a Jupyter Notebook, and you can just run your code in there. So Google's got a great one called Colab. There's another one called Data Lab that's paid for. That's on Google Cloud. And I just don't like having that little control. And I think my simulations might have taken too long to run, so I wanted this one. So then to use the TensorFlow stuff, I just go source activate. And I want the TensorFlow 3.6, so it's going to Python 3.6. So now we've got that. I've got this thing called DCGAN TensorFlow. And I wonder where I should demonstrate the code we're running. Let me actually demonstrate what it looks like when it runs on my own machine. And then I'll, just because I don't want to bugger up the models. Oh. How do you get rid of the side window, Celia? Control B, isn't it? It ain't listening to me. Haha, thank you. And there's a little script we need to run. I'm actually going to just copy it because I'm a horrible human being. I suppose I could run down here. Yeah, I'll do that. I could go history, but I thought it was a little bit closer. Stop laughing at me. I can hear it. Is it Derek giggling internally? Is it you? I can hear someone laughing at me. I'm paranoid. Just want to check this is the right one. Cool. Yeah. So I'm going to not going to show you it training. I'll show you it running first. And it looks similar. Oh, main.py. Yeah, well. Cool. So this is how you run their code. My code ran with the main file. And you can see we've got some processed audio files. We've got the data set is stored. We've got input height, output heights, and we're looking for JPEGs. Cool. And this is, like I said, not going to train it. This is a please work. Cool. I'll let that run. So this is actually not training it. This is using it to sample a whole bunch of images, which I'll go show you now. So I'm sure you guys want to see this damn thing work now. Cool, that doesn't matter. Okay, so on this box, I have a Jupyter notebook running, or I had a Jupyter notebook running. I'll just rerun it. Has anyone used Jupyter notebooks? It's a cool way of running Python code in like a browser, and it's really interactive. So you can be like output an image, output a graph in these kind of little paragraphs. So you code in little snippets. It's like the data scientist tool of choice for most people. I don't have to activate the thing, because I'm just going to look at some stuff. Cool. So I've got some port forwarding set up so I can actually look at this. Cool. So what it's doing is saved a whole bunch of images to samples. So I think test ranges are one of them. We can pick any of them. And what you'll see is, I think, 10 images against 10 images. It's like 100. 1, 2, 3, 4, 5, 6, 7. Cool. Each of those are a little album cover. And what's cool here is that they're not perfect. But I can still see stuff. So we could have trained this for longer. And there's certain things, like it's seen that there's almost a human there. So it's kind of come up with a person. What it's definitely learned is that you always have text. So you can see that this is trying to like mimic text here and there. What you can also see is things like this, where you've got a... remember I showed you those record covers where they don't actually have the full cover. It'll actually start predicting that. What's great is if you actually calculate the distances between these images and any other image, you're going to find that they're totally unique. They actually haven't been created or generated, anything like that, which is kind of awesome. And I quite like that. So you'll notice the one thing that, like I said, they're quite small. This is because GANs start falling over and the bigger you get. And they've come up with some techniques to get around that. So I don't know about you, but I would probably put that on an album cover. That one looks like it's even got like some sort of weird lion. This one's got like some sort of drawing. We've once again got these weird circles which keep coming back and forth. But yeah, so there we generated it. And that didn't take too much. Does anyone want to see some more? Yeah, I could just look at these all day. I don't know why. So we've got a whole bunch generated. What was that? Yeah, which is actually probably a problem somewhere. So they call it collapsing. So your model can kind of collapse on certain types of colors, and everything just sort of pops up the same color. And maybe album covers are all sort of the same cover. Oh, you're not disagreeing with me. Oh, that's the guy who does all the Pink Floyd ones. Yeah. Yeah. Yeah, what's interesting is this yellow. There's like a lot of yellow. I would never predict there's that much yellow. There's a lot of browns, which I agree with. You can see sometimes it predicts things that are really similar. So it probably means I needed more data. I only had 60,000 images. Next time I will train to 600,000 images and leave it for a couple of weeks. It's a good more. What I want to show you as well is what happens. They all look familiar, but not the same, but familiar. So this is I made this training montage. This is my GIF. This made me really happy. You can see it starts kind of gray, then this is a bit later, then that's a bit later, then that's a bit later, and then they start becoming real. They're quite large chunks between that, so it's not every epoch, it's every 10, 20, 50, however I felt like clicking. It's quite cool that you can see it's actually trying to learn. So yeah, that code is basically around a whole bunch of generators. Any questions so far? Because we're approaching the end. You always have a question, Reynard. Anyone else? Cool. So let's talk about problems. Problems with GANs. As you can see, these things weren't perfect. They never are. I never demo anything that works really well. Last one I did a talk about generating lyrics that are like the Beatles, and to be fair, they do sound a bit like the Beatles, and if a couple of people I know dislike the Beatles, so they were like, yep, that sounds like them. They'd end with a lot of like, yeah, yeah, la, 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 or something. There's a lot about love throughout them. And you can see it's kind of the same here. It's like, cool, so you're kind of getting there, but we're sort of dipping into uncanny valley, and you haven't quite figured it out. And that's because GANs are really new, and no one knows what to do with them. So, problems, non-convergence. Usually what happens with the neural network is it gets better and better and better and better and better until it can't get better anymore. GANs just kind of oscillate. They kind of play against each other, and they get confused, and they confuse each other. And they never actually come to a point where they're like, we're the best right now. And that just doesn't happen, whatever they do to them. Mode collapse is where they kind of all just fall into like the mode thing that's happening. So they kind of, you lose colors. The one stops training because the other one got too good, so then they just don't get any better. So as I say there's an imbalance between the generator and the discriminator causing overfitting, so they start looking exactly like their input images. And they're highly sensitive to hyperparameter selection. And you saw there's a lot of parameters. I have to choose momentum, I have to choose the type of activations, I have to choose the number of layers, etc., of which there are infinite different things you can choose. And if you choose one slightly off, it doesn't work. And I still don't know what's wrong with my original implementation, because the code looks nearly identical as far as you can get between Keras and TensorFlow. It's actually made me question Keras. I feel I have to go fix a bug somewhere. Here's a nice picture of the problems that happen with GANs. This is sort of a dog. And this happens a lot. And some of it's to do with problems with GANs, some of it's to do with problems of convolutional neural networks. So convolutional neural networks can't really count eyes. The filters don't get big enough. They've tried to solve this using a cool technique called capsule networks, which tries to kind of understand the image graph. This one doesn't really do that. So you can see we've got like some eyes and and who knows. It's a little bit scary. I find it scary. And like I said, one of the big problems with GANs is no one knows enough. So the guy who made them, I think he was 19 or so, I don't know, he was young, he was 21 or something, got his doctorate because he invented GANs, which worked, did something really unique. It was a really cool concept, but no one really understands like the nitty-gritty. So if you're debugging, you have a very hard time. Why is my GAN not working? I'll just try things until it works, which is, as we know from writing code, that is not always the best strategy. Although I do think some people code like that. We have come a far way, so we've got, this is where they started. This was 2014, I think is when they were made. Then we got something happening here, some really creepy dude, and then this. And this is the Celeb A dataset, which has pictures of people's faces. Celebrities' faces. So they used a GAN to generate people who look famous, and he looks reasonably famous to me. This guy less so. This guy, sure. Cool. So that was the presentation. Thank you very much for coming. I like questions. We do have a mic, so where's the mic? I'll have a mic pass arounder. Is it going to be Reynard, or is he going to ask a question? Julian, do you have a question? You're going to pass the mic around. No, you're passing it. Okay, yeah, sure. So if you want to go to the presentation, you can go to bit.ly/deeperdreams. You can always find me after the beer. And I'm going to do a shameless punt. Talking about album covers, I have a gig tomorrow and on Saturday, and releasing an EP, well, not an EP, an I don't know what it is. It's a vinyl, and it's an H-end vinyl because our songs are too long. As you can see, we're not quite generating album covers like that yet, but it's tomorrow at Mall Kiosk in Melville. So yeah, question. Reynard.
Okay, so what I wanted to ask is, you mentioned that GANs suffer from non-convergence, but what would that look like ideally? Because you have the discriminator and the generator model, which are constantly competing. So like you mentioned in the beginning, the one gets better and that prompts the other one to get better, et cetera, et cetera. So what would convergence look like in that context, ideally, even though we can't achieve it? Or is that an inherent problem with it?
No, so what it should do is they should both get kind of really good, but what tends to happen is they tend to get better at each at their own thing, and then something happens and they go, and they get better, and then they fall away, depending on what you're doing, and that's what I think happens. That's a good point. And if you can figure that out, you can probably change GANs. Yes, more questions. Julian has a question. Please tell me why something works. So Julian did his master's in convolutional neural networks, so he's probably, yeah.
Anyway, I wanted to know what your noise looks like, because you talked about the noise.
Yeah, actually don't show it, which is a good point.
That noise on the whole network, and then where's the image that's getting that noise? Based on what you put in the noise on the image, at what level the noise is having a problem on the generator and the discriminator.
Cool, so that's actually a good point. So there are actually some cool, I should have included them. They're cool ones where cool websites you can actually go to where they mutate the noise for you, and you can see how that changes the generator. And what tends to happen is that the noise is just, it's normally distributed noise over, we've got 100 latent dimensions, we call it, normally distributed, and I have seen happen is that it can sometimes pick up on different features. So that one dimension will end up controlling some part of the color, and that one other dimension will end up controlling something else. But I haven't seen any studies related to how that works. I'm sure they're out there. But like I said, you get some really cool ones where they kind of slowly morph the noise in different ways, and you can actually see the image mutate. They do a great one with cats. So you can see like cats, as they mutate the noise, the output will turn from one cat to another cat in a different position, depending on what it's doing. So it seems that they often get quite directly tied to features. What I wanted to do today, which you were trying to help me, but we couldn't get it to work, was basically show you the noise that we generated, and then show the image, and then kind of change that noise. But for some reason the code isn't running in Jupyter, so that was annoying. So when I get that fixed, I'll post something on Twitter, and then we can look at it. Anything else? Cool. Does that answer your question? Half. We'll talk afterwards.
Hi.
Hi.
So I pretty much show all the theory about AI, machine learning, deep, whatever, but like I haven't written a single line of code yet. So what would you recommend that's like a very simple hello world application or a...
So there are a whole bunch of them, but if you want to get into something like images, actually there's so many resources. You're probably overwhelmed by the amount of resources available. It becomes quite hard to pick. I would look at the Keras tutorials.
Okay.
They've got a whole bunch of them from beginning all the way through. If you're going to look at images, there's a data set called MNIST. It was the one I showed the 8. That's basically showing you how to classify numbers or generate numbers. If you don't want to build the neural network yourself, which generally you don't need to, you could start with something like scikit-learn, which actually has everything built in, and you just have to call the thing. So you just go dot, here's a neural network, and dot fit, and it'll fit it. And you'll see that the hard part with most standard AI applications is very little to do with the model anymore and everything to do with the data. And it's a nightmare and the bane of my existence, but it's always the data that's a problem. And you'll speak to anyone who works in machine learning, they spend more time on the data than they ever do on the algorithms, except with GANs, because they're temperamental.
Okay, thank you.
But yeah, Curious tutorials are really great. Google also released something last night, 2 nights ago, which contained a bunch of also their kind of take on it. I haven't had a chance to look at it, but it might be worth going through. But I know the Curious ones are very, very, very well explained. There's some of like the iconic bugs. Any other questions? Yes.
Hi. I just wanted to ask about the cost function for the.
Yes.
Is it a single cost function for both the generator and discriminator, or is it?
Yeah, they're both. So
or do they have
discriminator is
individual
using binary cross entropy.
So they are separate.
Yeah, but it ends up. They're not separate. So when the GAN trains it, it ends up being binary cross entropy because when we train the GAN, we put it in the combined network. And it's binary cross entropy because it's a yes or no. And yeah, so they actually end up on the same one because when the discriminator is binary cross entropy and when you put them together, it's the same thing again. So they've got another one. The one I actually wanted to use but also couldn't get to work for 2 weeks was called the Wasserstein GAN. Is it Strauss? That's a Wasserstein. Definitely a Steen there. The Wasserstein GAN is got a different loss function, and that loss function is actually better for creating better images. And it's a Wasserstein loss, and they also both use it. But the resulting images are a lot better, but it takes about 100 times longer to train, as far as I could tell. Yes?
Okay, yeah. So if they have a single cost function, what are we trying to optimize then?
So we're trying to optimize. It's a single cost function, but we use it in 2 phases. So you're trying to optimize for the discriminator, its ability to classify correctly, and when you put the generator in, it's the ability to trick the discriminator. And they actually end up, if you look at most reporting things, they end up averaging those just for reporting. But actually, if you do a batch of the one, backpropagate, and then you do a full batch of the other and backpropagate that. Yeah, hope that answers the question, sort of. Anybody else?
Hi. So you mentioned earlier that a lot of the techniques that we're using now are things that guys came up with decades ago.
Yeah.
And we're able to put them into practice now. Yeah. Do you think that is evidence of challenges in AI being overcome quicker and quicker? Because there are some people who take that idea and run with it and predict like a crazy future.
Waves. It's always waves.
You think it's like a...
They always talk about the AI winters. And there's the first winter, and then there's the second winter, and now the upcoming third AI winter is a thing. So it's kind of like we reached the peaks everyone had, and it's this problem, right? Everyone has these overhyped expectations of what it can do, and when they realize it can't quite do exactly what it promised, everything stops, funding stops, research stops, and this has happened time and time and time again. And it's just going to keep happening. And I think we will reach that AI research, because what tends to happen is there's a boost of research in like a new field, and then people need to understand why it works, and then it slows down, and a lot of theoretical stuff happens, and we don't see new algorithms as much as we studies about why it works. And I would predict that and also, here's the other thing other people don't know. Machine learning is just one field of AI. There's reinforcement learning, which is another field. Then there's kind of the more swarm side. And if you actually look at the boosts between all the things, when neural networks aren't interesting at the moment, so machine learning's taking a dive, some reason the swarm techniques will take like a rise, and it's almost as if they start using the techniques from the previous one within their own stuff, and they kind of play against each other. So will it just get faster and faster and faster? No, I don't think that's how the world works. It will get better, but like it's waves.
Cool, thanks.
Don't like invest in AI because it's useful, but like don't listen to, oh my gosh, we're gonna die tomorrow. No. Thankfully, there's things like laws that don't change fast, so we have to figure out stuff. And yeah.
Can we hope that blockchain dies in its first winter?
I think it did. I don't know. People are still talking about it, but like it pretty much died. It went from like everybody being like, "Oh, let's invest in everything," and now it's like a joke for the most part. So yeah, let's hope. I'm pretty sure it's over.
Any other questions?
Yes, there's one behind the pillar over there.
Hello. Yeah, I want to ask you a general question about artificial intelligence.
Yes.
So, like, my approach was that I divide AI into three things. So we have the brain, then learn and walk. So my approach is like you view AI as a person. So the brain, that's where you teach the code. Like you give the code, like how to understand things, everything else. Then learn is from data, normal data. If it's pictures, then you give it a lot of data. Then walking is like when a baby starts to work, you teach them how to work. So how would you recommend that approach to artificial intelligence?
So I think the way I would break it up would be, if we're talking about humans, I would break it up into perception, which is the ability to take in information and kind of make sense of it. So perception, our eyes, our ears. So a lot of deep learning is very much perception. But then in the brain, you've kind of got, in my mind, you've got sort of a lot higher level logic, right? It's higher level thinking. And it's more than just we look at an image, some sort of reasoning happens. And that's very different to what happens in machine learning. They don't really, there's reasoning, but it's very abstract. And reasoning is a very higher level function. So you can think of that, and that's closer to fields like symbolic logic, and deep reinforcement learning, sorta. And also with that, you could see kind of learning, the process of learning from what you perceive, the learning mechanisms. There are a whole bunch of ways of doing that. That's why machine learning is kind of a field. And walking, they've got something called reinforcement learning is kind of the closest you can get to how a kid tries to learn. It tries things, it fails, it learns from the failure, and then tries a different thing, pretty much. I don't know if that answered the question, really. Practically, if you start going into all the different fields of AI, you'll see that there's more than just that. There's more than just what the human is, right? Because I believe our intelligence isn't just solitary. We are intelligent together as well. So part of our intelligence is society. So then the swarm techniques come into play. Then there's a whole bunch of other stuff to do with just our plain-ass genetics. Our genetics say a lot. So then they've got a whole field on genetic algorithms. So I think it's more than just the person. There's a whole bunch of other stuff. And what you're talking about a little bit is generalized AI. And generalized AI is, or general AI. And that's like, how can you create an intelligent unit like a human that can do general things? Whereas in practice, we are nowhere near there. We are, in fact, I think some people are further, I think we're further from that now than we probably thought we were back in the day. Back in the day, we were like, oh no, we'll figure it out. Now I think we know a lot more about intelligence and how, general intelligence and how hard it is to achieve. So you'll see machine learning by itself will never be able to do what a human can do, and reinforcement learning will never be able to do what a human can do. And they're only trained on, I'm going to classify bottles of beer, and that is my purpose, and that is all I can do, because that's all you train me to do, right? So general intelligence is really, really, really hard. And it'll probably take a combination of techniques to get something like that. I don't know if I answered your question. I just went on like a rant. That's what I do. Anything else? Yes, the one over there. Getting more exercise, right? Not.
Speaking about general artificial intelligence, do you think that the fact that there are undecidable functions, does that make it impossible for us to ever get to general artificial intelligence?
What do you mean by undecidable?
The halting problem, for instance. Does that...
The whatting problem?
Halting problem?
Hopping?
Halting?
Oh, the halting problem. Oh, no, I don't... that's a good point. Would the halting problem affect them? Can we as humans predict the halting problem? Could be. I think there probably is something to that. Others would say you'd get around that by having multiple units. So there's a whole bunch of robotics thing, like researchers says that's stacked. So maybe the one unit can't tell it's going to halt, but maybe the others can. They're monitoring that unit and they know that program's going to halt. I'm kind of the belief that humans are just giant complex computers, so I think we'd maybe suffer from the same limitations. Yeah, you're asking for a really random opinion, but good question. Come answer it when you know. I have no idea. Cool. Anything else? Something less abstract? Like, what's the name of my band? Something, I don't know. Cool. If there's no more questions, thank you very much for coming. I hope it was useful. If my talking wasn't useful, then I hope maybe the slides or some of the code is a bit more useful. I will give a prize to whoever can fix my code and make it train properly. I don't know what the prize is. I'm willing to negotiate because it's driving me mad. Huh? Copy of the album, yeah. You can have a copy of my vinyl. Or another t-shirt. Cool. Thank you very much. Have a great evening. Enjoy some of the more beer, the drinks, or the food. And I'll see you at the next Rabbiteer session. Next one's in September.